This week's lecture is on the ocean margins or ocean basins, and it's going to be a tour of the ocean's bottom and the edges of the oceans where they meet the continents. So the map you're looking at right here is the famous 1965 map made by Marie Tharp of the National Geographic Society that shows the bottom of the ocean with all the water drained away. And after many, many years of studying it, principally by sonar before the 1960s, we got an idea that the bottom of the ocean was not as simple and featureless as originally thought. Look, there are giant mountain ranges, deep, deep trenches, pinnacle-type mountain things, volcanoes, you name it, it's got it. So let's look. The next slide is a typical cross-section of an ocean basin. The ocean's shown in blue. And look how, see the red words. It divides the oceans here into the deep ocean basin and then the margins. The margins being the edge of the continents. And then go down below those red words, continental margin, and see that the margin includes three parts: the shelf, the slope, and the rise. Okay. Here is another diagram. This is an odd one. It's called a hypsographic diagram, and it's complex, but try to give it a shot at understanding it. It shows the relative percentages of, first of all, land versus ocean. So notice that the percentage of the ocean by the width shown there is much greater than the percentage of land on planet Earth. And then of the percentage land area and the percentage ocean area, it shows the relative percent visually of how much mountains we have, how much flat land platforms versus all the other things. Again, one thing I always want to point out to people is that notice on land we have highland areas, mountains, and we have low land platform areas. In the oceans, we also have the same thing, we just have more of them. Continental margin defined the transition from the continents to the ocean, but in a geologic sense, the transition from continental crust to oceanic crust. Another way to phrase it would be granite dominance to basalt dominance, and this is almost always submerged versus seawater. The first comparison I'm going to make is an active margin versus a passive margin. An active margin coincides with a plate boundary, especially a convergent one. Look at the picture right here. You see there's the ocean, and you see high mountains in the distance, and then there at the shore you see a lot of large clasts, including rounded ones, but a bunch of irregular, angular-shaped ones as well. So mountainous areas, immature sediments right by the ocean typically define an active margin. Contrast that with a passive margin, and here I have just sort of a wetland, swampy area photo to look at. These are low relief, broad coastal plains, and the sediments here are very, very, very mature. Another way to look at this from our continent to the south, you're looking at a cross-section of the globe through South America, and South America on its east coast has a passive margin. Notice the transition from the land to the ocean is sort of a long sloping line, passive margin, and you'd find mature sediments here. Contrast that with the west coast of South America, which is a convergent boundary. So deep ocean trench, volcanoes, subduction zone, and you've got mountains right near the ocean and lots of immature sediment being delivered there. If you look around the globe, it's not 50-50. So the areas marked in purple are places where there are passive continental margins. Look, that's most of them. The places where there are active margins are not marked, and look here where it encircles mostly the Pacific Ocean. So this is why this is called the Ring of Fire in tectonic terms. There's lots of active tectonics, active volcanoes, earthquakes, active margins. Looking at the other side of the United States, here's a passive margin. Again, if you've ever been out here in the Carolinas and Florida, you know that it's lots and lots of flat real estate. You drive mile after mile and don't see much in the way of topography. Well, that continues out into the ocean for many miles until you reach the edge of the shelf, slope, and rise. And then remember, collectively, the shelf, slope, and rise are the continental margin. Well, how do we study this stuff? How do we know all this stuff? Several ways. The first, and for the past, say, 50 years, primary way has been we go out with big boats like this one and we drill. So that stack that you see on top of that boat is a drill platform, and they're not drilling for oil or anything. They're drilling to get cores of rocks to study. So the drill bit goes down through the water, hits the ground, the bottom of the ocean, drills into the rocks, and brings up a cylinder of the rocks that it cuts through. This picture here is a site marking all of the places where the ODP, the Ocean Drilling Project sites, went through 1994. Notice they are scattered throughout all of the oceans across the globe, near active margins, continental margins, in the deep, etc. The ODP is the drilling project that is part of a whole series of them. There was something called the DSDP, Deep Sea Drilling Project. That's a really old one. And now we are in something called the International Ocean Drilling Project. And collectively, the countries that support this, principally all the ones you'd expect in the United States, Canada, many countries in Europe, but also Japan, Australia, spend billions, that's with a B, billions of dollars to get this data for both hazards research and principally pure scientific research, but also resources. On the boat, here's just a few pictures. Here's a drill core going down, and so this drill bit goes down thousands of feet, and it augers through the rock, and it creates a cylinder of pure rock that goes up through this, and up comes those thousands of feet of rock. Here's a picture of one of the scientists on the boat. The boats typically are filled with both sailors, of course, and many scientists of different disciplines. And this one here, she's looking at the cores that come up, and looks like she has some sort of geochemical or geophysical measuring device, and she's going up and down this length of core here. Here's another picture. Usually the core, as it comes up, are these big long cylinders. It is immediately sawn in half. See the two halves here, and half gets archived in a library. Yes, there are core libraries. The other half is studied by different scientists. So some of them will look at microfossils in here. Others will examine the geochemistry of the rocks, the geophysics. And a lot of this is done on board on the ship as the core comes up. But then, as I said, these things are saved in core libraries, and they're saved forever, like books in a library. And they're studied by scientists from around the world ever after. So that's how we principally know a lot about these margins and the bottoms of the ocean. And we can make nice little cross sections like this. This is a cross section of the Atlantic coast margin, so passive. There's that big, broad, flat coastal plain, continental shelf, all of this. And we understand from drilling cores throughout here the layering of the sediments, the structures of the bottom, and the potential areas for resources, oil, gas, manganese nodules, phosphorite, all kinds of things. A different cross-section, this is in the Gulf of Mexico, so off of Texas, again, a passive margin, but the sediments are very different here. A lot of you know that the Gulf Coast states and offshore is a huge petroleum reservoir for the whole United States, for the world, and the different shapes of these continental margins give us the evidence that tells us where to drill, how much to drill. But we also have other ways to study the ocean bottom, principally by satellites. Just as sonar sent a signal, a ping, down from the surface of the water to the bottom and bounced back, and that's how the early tectonics people mapped the ocean bottom. Nowadays, we can send a ping, a hypothetical ping down from a satellite, and it'll travel through space first, then the atmosphere, then the ocean water, hits the bottom, comes back up, and now we get very, very accurate maps of the ocean bottom. The next bunch of slides are a whole bunch of cross sections throughout the ocean basins, and how you read these is the lines, like for instance here AB is the area that the satellite traversed to map. The cross section below shows the bottom of the ocean as revealed by this. So the signal goes all the way through the water and bounces back up, and one of the things it reveals is drop-offs, flat abyssal plain areas, and then in the central part of the Atlantic, you notice big highland areas. These are those mid-ocean ridges with volcanoes and shallow earthquakes, and it gives you basically a map or outline of the bottom. Compare that with a sort of simple drop, uplands, drop again, raise to the Pacific. Look across here. It's from C to D. There's all kinds, many high areas, low areas, etc., etc. Just some other sort of views from satellites. So here, the black lines, we're going to cross the entire plane of the view here, the whole map of the Earth. The oceans cross sections are shown in blue. The land is in red. So again, notice it drops off all this weird complexity. There's a deep ocean trench right at the side of South America. There's the high Andes of South America, active margin. Huge flat coastal plains across South America, passive margin. Big ocean basin, mid-Atlantic ridge. Here's it cuts through Africa, and you see a little bit of the Indian Ocean. A little bit farther north, and you see the deeper ocean basins shown here. Again, you see the ocean trench. You see the highest parts of the Andes. And again, the deep Atlantic, parts of Africa, parts of the Indian Ocean. Go farther north still, and now we're kind of cutting across just a little bit south of us through the United States. You see a little bit of the Pacific. Here's North America, folks. There's the high Rocky Mountains of the West, more where we are, the flat sort of central plains of America, the little blip of the Appalachians, passive margin of the Atlantic, and then there's the bottom of the Atlantic. Close up, just to show a couple of things in more detail. Here's again the Pacific Ocean off the coast of South America, the deep abyssal plains, a little bit of the Nazca Ridge, a mid-ocean ridge complex. There's the Peru-Chile Trench in this subduction zone, and then the high Andes. Okay, well, let's look at this now. Let's talk about different features of the margin. So the continental shelves. In this map here, they are shown with this sort of tan or orangish or beige color. And notice they fringe all of the major land areas. Where you have passive margins, they typically are wider and bigger. So passive margins around most of the Arctic, some passive margin over here, not a lot, and then passive margins on the east coast of the Americas, where you basically don't see much or very little at all. It's usually an active margin. Not always true. So let's define the continental shelf. These are the shallow submerged parts of the continents underlain by continental crust, and collectively it's about 7.5% of the Earth's surface. We've seen this slide before, just another picture. And another one here, just to refresh your memory, the continental shelf is the most landward part of these continental margins. A little bit more about the continental shelves. They can be very, very brief, or they can be huge, wide, many hundreds of kilometers or miles. The slope is rather low. If you go a kilometer of distance, you typically will drop only a couple meters. So it's really like a shelf, like a bookshelf. Most of these things end at about 140, 150, maybe up to 200 meters water depth. And we call that the shelf break. That's sort of the edge of the shelf. Edge of the bookshelf, fall off. Active margins, steeper and thinner. Again, back here, picture of that. These are sort of topography and elevation maps of different parts, sort of the red lines cut across the globe this way, and you can see the little line, they represent sea level, and where they are above it, where the line is above it, that's above sea level. Notice vast swaths here are just about sea level, and then where it goes below, it's bathymetry, it's below sea level. Notice on the edge of the Atlantic, United States in the Atlantic, these flat platforms extend outward into the ocean. So on land, flat coastal plain, out in the ocean, flat continental shelf. The continental shelves themselves are important for a whole bunch of things. When I talk about them in my paleontology classes, we talk about the origin of life being there, the most fossils coming from there. In the context for us, you need to know that these places have extreme amounts of resources. Resources meaning oil, gas, but also just life, like this coral reef you show here. Below that is the continental slope, and I'm not going to read off all of these different sort of facts here. Just realize that if you've driven on an interstate highway through mountainous area, the steepest grade that they allow by law on those interstate highways is 70 meters per kilometer, and that's about what's happening on the slope. So it's a noticeable break from the continental shelf. Cutting across these continental shelves are these deep submarine canyons. So on this map, these are topographic lines, or here bathymetric lines. You can see the flat continental shelf, and then where these lines are tightly packed together, that's the break, that's the shelf, that's the slope. But notice you have these big linear cut features going across here. These are submarine canyons. And when sediments are washed off of the continents here, usually these things are connected to a river on land. That river water, all that sediment gets onto the shelf and whooshes down these submarine canyons through big canyons here, and then flushes down into the deep ocean basins. These things can extend for hundreds of miles and have tremendous depths. This picture is more diagrammatic, showing the edge of the continental shelf and then this submarine canyon cutting across and flushing into the deep. Another view, topographic wise, just to show, this is the Hudson Submarine Canyon in the East Coast, and again it makes these linear features, these cuts, these breaks across the continental shelves. A more beautiful mapped version is on the West Coast. San Francisco Bay is up here, Monterey, California to the south, all beautiful coastal areas. But below the surface of the water, you have this very deep Monterey Canyon. And sadly to say, a lot of the ocean communities here, the cities that are here, how they get rid of their garbage. They have all kinds of regulations that limit the amount of places where they can put it in landfills, like we do here in Wisconsin. Instead, it's barged out by boat and dumped in the water, which hits these canyons and then flushes down these canyons into the deep. So Californians, for all of their environmental consciousness, they do this in sort of an out-of-sight, out-of-mind fashion to avoid having landfills on land. So submarine canyons are used by them for that purpose. The sediment that flushes down here goes along with the garbage in these things called turbidity currents. So for years, long periods of time, nothing happens, and then the sediment builds up enough where it whooshes down and makes what we call a turbidity current. The beds of rock at the bottom of the deep ocean are turbidites, and they have a very particular shape. If you look at these cross sections, look, the Monterey Canyon, look at that relief from the highest point to the bottom. Compare that to the Grand Canyon. Again, the canyons of some of these submarine canyons are bigger than what most of us assume are the largest canyons on Earth. So if you've seen the Grand Canyon and you know what a big hole that is, think about this. The Monterey Canyon, the Hudson Canyon, all of these big submarine canyons that are cutting across the shelf are bigger. They're bigger. Below the slope then is the rise, and this isn't on all of these things, but think about it. If the sediment cuts across the shelf, whooshes down the submarine canyon and gets dumped, it usually makes a pile of sediment down here called the continental rise. And as I say there, they're most often found in these passive margin areas. Now the deep ocean basins. After we've gone through the margins, you've got the deep, and the deep is all of this area out here, and there's a lot of complexity there, but I'm just going to quickly go through it today. So margin area and then the deep. Huge abyssal plains with not much going on, but then all kinds of irregular hills, mountains that have weird names, guyots, islands, of course mid-ocean ridges, a lot of stuff. Just a short list of some of these things. The mid-ocean ridges, hydrothermal vents. Some of you know about those, but we'll wait and talk about those a little bit later in this class. Arcs, trenches, seamounts, volcanoes, abyssal plains, you name it, it's there. This map just kind of showing the relief in meters, and then showing the deepest parts of the ocean basin are shown in this sort of magenta-y type color. What else? The ocean trenches from convergent boundaries. And looky here. If those submarine canyons are deeper than our Grand Canyon, well, then by all means, these deep, deep, deep ocean trenches are bigger still. Look at this. Mount Everest. Most of you know that is the highest mountain on Earth. It can fit into one of these ocean trenches. This one's called the Challenger Deep of the Marianas Trench, and still have almost a couple of miles of water above it. So again, I always say this, the biggest features on planet Earth, biggest mountains, deepest canyons, they're dwarfed by what is in the ocean. The next slide is just a few sort of samples of these things, different named trenches around the globe and their depths, their lengths. Notice some of these things go on for thousands and thousands of kilometers, and they're very, very thin. The area can be huge. Just another picture here. So here's Japan, and then off the coast of Japan, the northern part of Japan, and then skirting out into the ocean, this sort of darker blue line in the ocean, that's one of these long trenches where this oceanic plate is being forced under this one. Over here then would be another set of trenches. Down here another one. The Pacific is pretty complex. Trench regions around the globe, around this ring of fire. Notice almost all of these are in the Pacific Ocean. You have some in the Indian Ocean and a couple here in the Atlantic, but for the most part in the Pacific Ocean. Contrast that with the oceanic ridge system, divergent boundaries, and they're everywhere, but they're not where those trenches are. So oceanic trench here, oceanic trenches here at convergent boundaries, and here's the opposite, the divergent boundaries. Just another picture with the ocean water drained out of the Atlantic. The upper left would be the United States. The lower right would be Africa. There's the mid-Atlantic ridge cruising through the middle of that, and then some complexity, different hills and things over here. Notice you can see big, wide, flat continental margins, passive margins here, England and Ireland, and as we've said before, off the coast of the United States. And that concludes this. This takes us back to the map that Marie Tharp made in the 60s. This complexity, all of this you see at the bottom of the ocean, is there because of plate tectonics, but also sedimentation, which is going to be the stuff we're going to study next week. So plate tectonics makes the hole in the ground and shapes a lot of these different features of the bottom. Big, giant ridges, trenches, etc. But then we've got continents that are exposed to the atmosphere and weathered, and they are dumping sediments all through here. Next week.